Thank you very much, Julien. Uh, right, so I'll talk about some mostly work from a long time ago, but also some recent ongoing work. Uh, and this is focused on the idea of what now come to be called Planckian dynamics. That there's this, unproven bound that is believed to be satisfied by most systems that some kind of relaxation time is greater than or equal to h power over kt, uh, and as temperature goes to zero. And we're interested in a regime where this is the equality, it's an equality. So that happens in gapless systems with strong interactions, in particular in conformal field theories. But there's also been a lot of phenomenological evidence for some bound like this in the transport properties of strange metals. That's not something I'll talk about today, but that's also something we've thought a lot about. Uh, with strange metals, you have Fermi surfaces and strong breakdown of relativistic invariance. But so that makes the problem quite different in some ways. But it's curious that you get very similar bound, experimentally anyway. So one of the big issues, what this makes a very difficult problem, and let's just talk about conformal field theories for the rest of this talk. Even for conformal field theory, this is a very difficult problem. Naively, you would think, we have all these arsenal of tools like epsilon expansions, large N expansions, and bootstrap, and those are given many results for CFTs in higher dimensions with amazing accuracy. But here I'm talking about real-time dynamics, and if your only scale is temperature, and if you're doing imaginary time calculation, which is where all of these methods that I mentioned work extremely well, then for imaginary time calculation, the smallest frequency you have any information is 2 pi kt. And it doesn't matter how small you make kt, you're not going to become smaller than that. So if you're now interested in the real-time behavior at times longer than kt over h bar, there's really no well-defined way of computing it. And all of these methods that I mentioned, certainly for the epsilon and the large N expansion, you can show quite explicitly that the operation of expansion and the analytic continuation to real frequency fail. So that's kind of what I'll show you. And it seems similar things also apply to Bootstrap, but let's see, maybe there'll be some creative ideas in Bootstrap that allow you to analytically continue to real time in a sensible way. Okay, so I'll talk about two models, both of which have experimental motivation. First, I'll talk about the Ising model in 2 dimensions. Here, the experimental motivation is relatively recent. So these are experiments on Rydberg atoms, which have a ground state and an excited state. And so there's a laser that takes you between these 2 states, and this omega is the Rabi frequency of that transition. And there's a detuning between these 2 states. I guess I'll show that here. So there's your ground state, and there's your Rydberg state. You actually need 2 lasers to go up there. And this detuning is the difference between the level you think you would reach from the laser and the actual level. That's what delta is. So you go in a rotating reference frame, and the rotating reference frame, you don't have to worry about the laser at all. It's as if this ground level has been moved up to that level. Okay, so now the basic feature is this term here that makes it very interesting, that there's a repulsion between 2 atoms if and only if they're both in the Rydberg state. And there's a negligible repulsion if they're in the ground state because the Rydberg state is so much bigger. So this is a van der Waals interaction. And so this gives you a way of manipulating the qubit. So in each site, you have a qubit between these 2 states. And now you can manipulate it by this Rydberg interaction. So that's been a very rapidly developing field in the last few years. One aspect of it is quantum simulations of Ising models and spin class models. But much of the attention is focused on doing quantum computing, which I won't talk about at all. But I think, in the near-term application where these can be really useful for something is precisely for the kind of problems where I'm talking about. So you could also think of this in terms of a boson, where the ground state is no boson and the Rydberg state is one boson. So this is another way to write it. And there's a hardcore repulsion. These are hardcore boson. There can be only one or zero boson on each side. Let me skip that. So when you take a system like this on the square lattice, so what you can vary is the detuning here written as small delta. And this is the RB is, I guess, the strength of the interaction. I've forgotten exactly how you vary that. I should know this, but okay, it'll come back to me. Anyway, so RB is, I think, related to this. Let's see, what is it? Yeah, it's some way of tuning this interaction here. Okay. Anyway, so there's a certain regime where the ground state is this checkerboard. This is our DMRG calculations of Ryan Samazdar. You get a checkerboard and many other complicated situations. So here, every yellow is the atom in the Rydberg state, and every black is the atom in the ground state. And there's two possible states that it can find. So what we're going to look, this is some experimental measurement of these things. So what we're going to look at is this phase transition here, where you vary the detuning and you go from the checkerboard state to a completely disordered state. So that's an Ising transition because this particular state has a twofold degeneracy, depending on whether the Rydberg atoms are in the white squares or the black squares. And so this is really the first time we have a handle on just looking at the quantum Ising model and a quantum phase transition in the Ising model. Okay, so right. So this is some measurement. These are the correlation functions. It is a perfectly ordered state, and then you do the sample. They cool the sample different ways, and then this is the 2-point correlation function. And that's the size of it now. They can do much bigger systems now. And from the way the correlation function behaves as a function of detuning, they actually look at some Kibble-Zurich type scaling. You can read off the exponent nu. So this would be the exponent of the 3-dimensional Ising model, classical model, which is pretty close to 0.6, around 0.63, and that's roughly what they see. Okay, so this is a more recent paper on the dynamics of the system. So what they do is they set up the initial state in a given checkerboard at different values of the coupling, and you let the system evolve and look at the average of the autoparameter, the staggered autoparameter. And what you see are various oscillations as you cross the critical point. And from that, you read off a frequency of these oscillations. So if I think this is some scalar field, which is the Ising field, then there's some potential like this, and this is the ordered side, and that's the disordered side. And this frequency is what you'd call the mass gap. So the system is, has an energy gap on both sides, except there's no Goldstone mode. And so there's a mass gap on the ordered side and the mass gap on the disordered side. Here's the frequency. And what you do now is you go a certain distance to the left and you go the same distance to the right, and you look at the ratio of the two frequencies. So that's this quantity here. You pick a value of x, and then you look at the ratio of the frequencies above and below the critical point. And so this, as x goes to 0, is supposed to be a universal constant. It's known, well, to, I think, one loop or maybe even two loops, not exactly this quantity, but a related quantity that's been computed in the epsilon expansion. I'll mention that in a minute. Okay, so this part of the talk, I think I will skip ahead. I can post a note. These are lectures I gave at a school. So the kind of model we want to work with is this model here. You have qubits on some, we're not going to work with the Rydberg atoms. We just take a very simple Ising model, where this is the DESY interaction, and you're varying the transverse field, which acts in the x direction. And G is the parameter. When G is large, you're in the x direction. Where is the picture? Anyway, and when G is small, you're ordered in the ferromagnetic state. So this is the model we're going to study. And here I have a long discussion of which is in my book of quantum phase transition. So I'm just going to skip through it. How to relate this to the 5/4 field theory. So you get various particle states. In the ordered states, you have two degenerate ground state, and then you have some flip spin, that's your particle. And in the disordered state, well, you again have spins pointing to the right, and then this spin pointing to the left is your particle. Okay, so you can look at the energy gap of these particles in some perturbation theory in G. I'll skip that. And then what you'll find is something like this. This is the energy gap on one side where you can do a large G expansion. This is the flip spin from the x to minus x. And these are little bubbles. You can do a small G expansion. And the question really is what happens at the critical point, what happens to these energy gaps? So what we know then from the field theory mapping is that both gaps vanish at the same point. And since it's a relativistic field theory that you derive, Z is 1, and nu is the critical exponent that determines how the energy gap vanishes. Okay, so this is the part I'll skip. You can map this near this critical point where the energy gap is becoming small. You can map it onto a continuum field theory. And it's basically exactly the familiar. So this is our field theory in D spatial dimensions. Phi is canonically conjugate to phi, so you can write it as a time derivative of the Lagrangian. It's a relativistic field theory of just one scalar field. Okay. So if you take this very simple theory and you look at the energy gap as a function of the tuning parameter R, even in just classical analysis. So for R positive, you get a mode here, which has frequency square root of R as 0 momentum. And the square root tells you that the exponent nu is 1/2 in mean field theory, as you know. And if you go on the other side, and again do the same calculation for small r, you will get a frequency at 0 momentum, which is square root of 2 times r. So it's larger by a factor of square root of 2. That's simply a property of a quartic polynomial, and it's independent of the value of u. Although the minimum depends on the value of u, the frequency here does not. Okay, so that gives you this number for f of x, which they measure to be 1.9, and in just mean field theory is square root of 2. And there are various epsilon expansions, which I guess I mentioned somewhere, which give you actually a number not so far from 1.9, which are cited in this paper. All right, so that's, very nice. We're starting to see some evidence of the two phases and also measuring this universal mass gap ratio. But now we are interested in the critical point, which at least in this paper has not yet been studied, but I think in the future, Tom Vanowitz in particular is planning on really looking at that more carefully. So it's that critical point that I'm going to address in the rest of my talk. Okay, so this is the field theory, now written out as a Lagrangian. And then to this, you can interpret this field theory as the field theory of a classical Ising model in 3 dimensions. And so you can just use the epsilon expansion, the larger expansion of the Wilson-Fisher theory that I'm sure all of you know very well, and a very standard set of results. But now I want to focus on, so that would be at 0 temperature. With all my discussion so far has been at 0 temperature. So there's a phase transition from a ferromagnet to non-ferromagnet. And this critical point is described by the 3-dimensional Wilson-Fisher CFT of the Ising variety. So now when you turn on a finite temperature, what will happen is that the ordered phase is stable to temperature, because the Ising order can be stable in 2 dimensions at finite temperature, unlike in 1 dimension where it disappears immediately. When I say dimension, I'm always referring to spatial dimensions here. So then there is a phase transition, and in the vicinity of the transition, you get classical Ising behavior, which is in spatial space dimension 2. So this line has the same exponents as the Onsager theory, so which is nu equals 1 and eta equals 1/8 or something like that. So this line has the Onsager exponents, is how things determine. But this point is the Wilson-Fisher exponents in 3 dimensions. And everywhere along this line is the Onsager exponent. Furthermore, but if I now look at the behavior here in the vicinity of this point, the best way to think about it is in terms of the 3-dimensional critical point. That's the unstable critical point here. And so you can write down the scaling form. And this 3-dimensional critical point has 2 relevant directions. One is G minus GC, and the other is temperature itself. And temperature, being an inverse length, has scaling dimension of -1, whereas G minus GC has scaling dimension of 1 over nu. So that's a property of this critical point. And in this critical point, then you can just, as a function of frequency and temperature, just the usual scaling arguments with 2 relevant variables, you can write down the scaling form, where phi is the universal function. So this function, this entire function phi, even at finite temperature, is a property of this point. But where's the Onsager exponent? Well, the Onsager exponent happens at a very particular value of G minus GC. So from this, you see that there's a singularity in the scaling function. And the singularity of the scaling function, as G minus GC approaches this point, at some value of this third argument, it's equal to some number, which is also universal in a sense. I mean, if you normalize G minus GC correctly. So there's some singularity of this function as a function of the third argument that determines the position of this boundary. And the singularity of the function itself near that point is given by the 2D exponent. But the whole function is universal, not just near the single point. And in particular, I'll focus here on this pink region, where in fact, the temperature is much bigger than G minus GC. So to 0th order, you can just put this argument equal to 0. And then you're in the pink region, where you have entirely the physics of this critical point and its finite temperature relaxational dynamics. And that has nothing whatsoever to do with the dynamics of the 2D Ising model, which would be along this line. This would be the 2 plus 1D quantum Ising model, where roughly speaking, quantum and thermal fluctuations are equally important. So that's the Planckian regime. Okay. All right, so why can't we compute something? So when you do epsilon expansion, so let's go along this line and just do the epsilon expansion. Okay, so at first order, you will find that there's a mass, you get a mass gap here. So that's up order epsilon, and so some universal number. So that looks good. There's a thermal mass. But we're interested in we're not interested in, this mass gap is totally fake, of course, because you have a gapless system at 0 temperature, and all you're doing is raising the temperature, and raising the temperature never induces a mass gap. It just gives you lots more excitations which can interact with each other. So the fact that there's a thermal mass, it's not really a mass gap. There are other terms that will give you damping that do not appear at 1 loop order. So when you go to 2 loop, this is what you find. You get an imaginary term in real frequency. It has this rather strange sine omega dependence. It also scales. It's everything's of order energy squared, so it's some universal number. So that looks like damping, but it's a very strong form of damping. It's sine omega as omega goes to 0 when omega is smaller than kT. And that's surely unphysical. What you would expect, just from general arguments, is some dissipative relaxational system it should behave like a damped harmonic oscillator. So there's some natural frequency for the oscillator, which is determined by temperature. And there's also a damping frequency, which I call here gamma, which is also determined by temperature. I actually have gamma is a pure number, just dimensionally. So this gamma is a universal constant. So what you really expect as omega goes to zero, even here, is that the low frequency behavior of chi inverse, the leading term, this is higher order in omega, the leading term of chi inverse as a function of omega is a term linear in omega, which is pure imaginary. And you can normalize it, at higher order, there's also various eta corrections and so on that only affect things in the front. This is this eta over here that I've ignored at this level. But you can take that into account and properly define it in a way that gamma is a pure number. So this is the challenge for theory, and I think maybe experiments can now, in the near future, I hope, measure this gamma. What is the value of gamma? So this is a much, much harder thing to compute than this f of x. That's a solved problem that you can do even in Monte Carlo in imaginary time, but there's really no way of doing real-time dynamics even in Monte Carlo to get this number. There was a question, maybe?
Yes. Can I ask in which sense it is universal, this gamma?
So I have to be a little bit more careful. It's universal because it's just like any critical exponent. It's a number, pure number it's a number characterizing the Wilson-Fisher fixed point, of which we do not know what that number is.
So it's universal in the Ising class of...
Yes.
Okay.
Yeah, for every n, there'll be a gamma for the ON model. So more precisely, to be perfectly precise, which unfortunately wasn't here, what you have to look at is chi of 0, 0 multiplied by d chi inverse d omega. So you have to normalize it by the static susceptibility. That gets rid of the eta stuff. And once you have normalized by the static susceptibility as 0, 0, and get rid of the eta, then the number is universal. So here I've written it in a form where eta was 0. Sorry, I should have written it more carefully. But eta is small, but it's non-zero. But that doesn't make gamma non-universal. It's some time. It's just a rate. So it has to be, it's a Planckian dissipation rate. Okay, so yeah, I guess I've already said that. So let's see, I'm doing time. Okay, good. So I just tell you about some old ideas that we are now improving, but of how to do this. How would you estimate this gamma? And so even numerically. So the main thing you rely on, okay, let's assume epsilon is small, and the same thing happens for large n also. Then what you notice is the characteristic frequency in all the propagators is square root of epsilon times temperature. That's coming from the thermal mass. Okay, so that's the frequency, the natural frequency of the system. And so for small epsilon, h bar omega is much smaller than kT. Okay, not by much. For epsilon equals 1, it's not smaller, but this is a thread we're going to hang our hopes on. So it's smaller than kT. Now, in h bar omega, the important frequencies, which are smaller than kT, if it's smaller than kT, then you have classical behavior, because the fluctuation dissipation theorem, as you know, when h bar omega is smaller than kT, just becomes a classical fluctuation dissipation theorem. So the idea is that perhaps if you only focus on the low frequencies, you can use a classical description of this quantum critical dynamics, but it's only justified for a small epsilon. And the end epsilon is all 1, so that's okay. But that's what we have. That's the one method we're going to use. I'll mention some other methods a bit later. Okay. Right. So what do you do then? So the idea is the following. So imagine you're in this region here. So we're interested, first let's look at the static properties. So the static properties, everything is cut off by temperature. So imagine you integrate out all the finite frequency behavior. So if you integrate out to leading order in epsilon, you have a critical point and you integrate out all the finite frequency mode. Then you'll get some effective theory of just the zero frequency mode, which will be a classical 5-fold field theory in 2 dimensions. So this is the classical theory in 2 dimensions now with 5-fold. And the reason it's 5-fold is because epsilon is small and the underlying theory only has a 5-fold coupling. Of course, if you go to higher order than epsilon, there'll be other terms here. So this is the field theory we have to solve. And if you try to look at what's called the Ginzburg parameter, which is how important is U as R becomes small, then you find it's of order 1. So you have to really solve this theory exactly. You can't, there's no approximation. But no worries. I mean, this is just a classical field theory in 2 dimensions. We can just put it on a computer and solve it. No trouble at all. So this is the part we're going to do numerically. And in fact, I'll mention the name. Julia Way in particular has been working on that. And I also did a little bit in this old paper. And from that, we're going to compute, say, some equal time correlation function, or zero frequency correlation function.
Excuse me, I got
Yes.
confused about the logic. This is just the usual computation of the thermal mass, isn't it?
No, so this is, I want to compute, let's say, zero frequency correlation functions.
But well, that's just the 2-point function at zero frequency. That's like related to the thermal mass at small momentum. How does that shed any light on the quasi-normal mode, on gamma?
It's not yet. It doesn't. So, but this is, I just want to pick, this is to be done to fix the values of R tilde and U. I can compute R tilde and U in the epsilon expansion, but I'm going to use a hybrid approach where I just take this theory and solve it exactly and determine what R tilde and U are. I mean, what you have to do is you have to match certain properties of the full 3D model with this reduced 2-dimensional model. Okay, but let me address, yes, I won't go into the details of the matching procedure. So, but let me just describe the theory. And then we can figure out how we're going to fix all the coupling constants in the theory. So here's the proposal. First, we assume that in the classical theory, another peculiar thing is in classical theory, equal time correlators are closely connected to zero frequency correlators because of the strange form of the fluctuation dissipation theorem. But more formally, this is the zero frequency correlator. So let's say I'm going to describe all zero frequency correlators by just solving this theory, where for now, I won't tell you how R tilde and U are determined. But this theory is not, in fact, it needs a mass renormalization because it's a continuum theory. There's a mass divergence. So you do have to take that into account. And that's really the only divergence you need to worry about. There's a renormalized mass R, which just comes from the one loop divergence. So you have to take that into account. And then you have a universal theory, continuum theory, which only depends on the value of R without the tilde and U. Okay, so let's assume you can solve that numerically. All right, so now how about the dynamics? Well, the dynamics is what I'm going to do is I'm going to just take this classical quantum field theory here. Here's the quantum field theory with a canonical momentum squared. I'm just going to replace now the commutator between pi, phi, and phi with a Poisson bracket. So that means what I have to do is the following. I take some ensemble of initial conditions defined by this partition function. And then I take this Hamiltonian where now there's a Poisson bracket. And I just evolve forward in time. And then I average over initial conditions. So that will give me, in the end, some estimate of this gamma, this solution of this classical dynamical problem. Now, this mapping becomes better and better as long as the natural frequency is smaller than temperature. And when natural frequency of order temperature, this is not very accurate. Well, we don't know, But here the hope is that, for example, this singularity, the fact that it's sine omega rather than just linear in omega, it's coming from infrared divergences. So the dominant effect is from the low frequencies, even when epsilon is equal to 1, let's hope. So perhaps this classical dynamical picture is not totally great. Anyway, so that's kind of what we are working on right now. I mean, I outlined this procedure here. Now we have an improved matching procedure. Now you have to determine all these coupling constants in terms of the properties of the 3D Ising model. I did that here using the epsilon expansion, but now we think we can do it exactly because you can just simulate the 3D Ising model too. And so you do two simulations, one of the 3D Ising model and one of the 2D 5-fold field theory, and then you match the parameters. But these simulations are all in imaginary time, so there's no issues. And then finally, the only thing in real time was the integration of these equations of motion. Okay, so this is something, as I mentioned, I've been working on with Julia Wei and also Matt Dordelson and Anders Sandvik. And hopefully in the next few months, we'll have a paper describing this attempt to finally get some estimate of gamma that hopefully is reasonably reliable. Okay. All right, so now let me talk about the second problem. So that's it for the Ising model. Any questions on the Ising model? All right, so there's a similar issue in the superfluid insulator transition. It's basically the n=2 case of the Wilson-Fisher fixed point. And you can ask the same questions there, but there's a new question that appears when you go to the n=2 case, because there's a conserved current. There's a global symmetry, a U1 symmetry, and a conserved current. And so we're going to focus on that conserved current because that's, again, something you could measure. It's related to the conductivity of the superfluid insulator transition. So in this case, we're going to talk about the superfluid insulator transition, in fact, of bosons. This was work about 10 years ago with Immanuel Katz, William Krempa, and Eric Sorensen. Okay, so this is the basic system that studied first in Emanuel Bloch's group and since then by many other people. You have bosons moving in a periodic potential. Again, these are rubidium atoms. Previously, for the Ising model, these are rubidium in laser tweezers. These is rubidium in optical lattices. And you can change the depth of the periodic potential. So when it's very deep, the atoms get trapped, one atom per site. They repel each other, and so they like to spread out this way. But when the depth well is not too deep, then they start to tunnel, and then you can get a superfluid state. So this phase transition also is described, fortunately, by relativistic conformal field theory for the two-dimensional case. Yeah, so here's a few more details. This is the Bose Hubbard model, where NJ is just the number of bosons on each site. And this is the canonical. So the model itself is not relativistic at all, but near the critical point, like the Ising model, it becomes relativistic. And in this case, it's very important that the density of bosons be exactly an integer. So there's one boson per site. If you work at any other boson density, then you're not relativistic. It's only in this case that, as you'll see in a minute, there's a possibility of a particle-hole symmetry. So there's both particles and antiparticles, which asymptotically close to the critical point have the same dispersion. That's what you need for relativistic invariance. So if this is the insulator, where atoms are trapped in a well, then the excitation, there's a particle excitation, we add a particle and move around. But there's also a hole excitation, which is an empty site. And so that's what makes it relativistic when the density of holes and the density of particles are equal. So the ground state is 1 per site when U is much bigger than T. And the trivial ground state when U equals 0 is a very different ground state. So notice here it's product on B dagger I on each site. Here, you put all the bosons in the 0 momentum state and raise that to the power n. So that's the ground state when U equals 0. So the ground state u equals 0 and u equals infinity, and we're interested in what happens in between. Okay, so there's some quantum phase transition, and that's okay. There's a condensate in one case and not in the other. And then you can write down, again, without derivation, the Wilson-Fisher theory, but now for a complex scalar. And so now the main difference is that now there's a U1 symmetry. So in the insulator, there are two types of there are two modes, one here and one there. And those are basically linear combinations of the particles and the holes. That's why there's two of them, unlike one for the Ising model. And here you again have two. One is the Goldstone mode, and the other is sometimes called the Higgs mode, although there's no gauge field here. Okay, and in fact, just like in the Ising model, they measured both the modes here, and they didn't actually in this paper measure the ratio of these two, but I think again it's not so far from the Ising value. I'm sure they can do that much more precisely now. This is 2012. Okay, so what I want to focus on is again the dynamics. So those are zero temperature behaviors. I want to look at the dynamics now I've already said all of this. So near this critical point, this U goes to U star. Okay. So at finite temperature now, again, you have a very similar phase diagram, except now this is not an Onsager transition, it's a Clausius-Thouless transition. And this is described by the O2 Wilson-Fisher critical theory. And now you can actually do, I didn't mention this for the Ising model, but you can do kind of a classical, Boltzmann description of both the dynamics on the two sides. Here you have some dilute gas of particles and holes. So you can write down a Boltzmann theory for that. And here you have to use other classical descriptions involving Landau-Ginzburg theory and vortices. But again, because of the presence of a condensate, it's also the classical equation is valid at the natural frequency that you're looking at. So where classical description breaks down, of course, is here where there is no Boltzmann-like description of the quantum critical dynamics. Okay, so one of the things you can do is compute the conductivity. All right, so this is in the epsilon expansion or the large N expansion. So what do you find? Well, so the conductivity is the current correlation function in the Kubo formula divided by frequency. And this is the real part of the conductivity, which is the dissipative part. So you find actually something very strange as a function of omega. It's a universal function of omega over t. Well, what you find is the following. So this is for free particles, although I do include the effects of the thermal mass. So there's a thermal mass gaps, and that's in fact this. And above the thermal mass gap, you can create particles and holes. We got finite frequency, just creating the excitation, and this is just the cross section for creating such excitations. And this number, it goes to a constant out here. At omega much bigger than t, it goes to a constant. And that's the constant, that's also a universal number. So I don't know if I said that anywhere. Okay. I'll get to that in a minute. Okay. In fact, the whole function is universal, not just that value. It goes to a constant here, but the whole function is universal. I'll discuss in a minute. But the other thing is, normally you just measure the DC conductivity. That's what gives you the resistance or something. In fact, the DC conductivity is infinite. So there's a delta function at zero frequency. What is that coming from? Well, so you have a system at finite temperature. So there's some pre-existing gas, thermally excited excitations, which are in this case free particles, which have a linear relativistic dispersion. They are always excited. And when you put an electric field on, they just start flowing. Since they don't collide, it's free, they start flowing forever, and that gives you an infinite conductivity with a delta function. Okay, the simple thing was overlooked by several papers in the condensed matter literature, but really that's what you get when you just do a simple free particle calculation. So now we have to go beyond free particles. And so you can do, in this case, again, an epsilon expansion and try to see what's going on. So the point you take here, you have nearly free particles, but they interact weakly when epsilon is small, because U star, the function U star, is small, at least in the epsilon expansion. So we assume that U star is small, and so then you have a weakly interacting gas of thermally excited particles. Well, that's exactly the conditions under which you can apply the Boltzmann equation. And so we solved the Boltzmann equation in this paper, and we figured out that this delta function broadened into some Lorentzian-like shape. So the Boltzmann approach is only valid over here. And the width of this is basically given by U star squared times temperature, or this is in dimensionless units, so it's just some universe. There's some width with some of order epsilon squared that we computed in this paper. It's very narrow and very high. And the conductivity is about 1 over epsilon squared. And then out here is where you can just use the bare epsilon expansion. You can just, and I will show you a little bit more about that, what goes on out here. So this is the easy region. This is the hard region. So again, omega is bigger than or smaller than kT. And here you have this, at least for small epsilon, a Boltzmann-like description. Okay. But as I mentioned earlier, the whole function itself is universal. Even the scale of it is totally fixed because you're dealing with a conserved quantity. There's no anomalous dimensions. So we'd love to know what this function is as a function of frequency over temperature. So it has a constant limit at high frequency, and at low frequency, it seems to be constant, at least in this calculation. But I think Powell Copton talked out that there are some long time tails in hydrodynamics that give you a log divergence in the function. Nevertheless, it's still a universal function, but I'm not going to say more about that log divergence. Anyway, so if you do the 1 over n expansion, you can again get some estimate of this, which you don't believe very much because you're assuming things interact weakly and the sigma naught is about n. But here you kind of believe it. You get a number of about pi over 8. Sigma, it's called sigma of infinity. And this is one place where bootstrap has really now killed the problem. So in this paper by Chester et al., this is the estimate of this sigma of infinity, 0.355, which is not so far from the 1 over n expansion. And there was also Monte Carlo work, which is again pretty close to the bootstrap. So that's very nice that this is starting to come together in the value of sigma of infinity. But really, the rest of my discussion here is, what about sigma of 0? How can you determine that? I've shown you the epsilon expansion gives you a number of order 1 over epsilon squared, but I'm not sure I believe that very much. I don't think it's terribly accurate. But anyway, okay, that's what we have. Yeah, so also in the large n limit, it blows up as n goes to infinity. All right. So in the paper with Ami Katz and William and Eric, we proposed another way of thinking about this, where we use holography. So, this is kind of the usual thing that you do when you do condensed matter physics or Glouon physics. You identify some quasiparticles, you compute their scattering elements, and then you compute them, put that whole thing in a Boltzmann equation, and then you solve the Boltzmann equation to get transport properties or other relaxational properties. However, what happens when you have strongly interacting CFT? That's also a useful starting point even for the Glouon plasma, which is it's supposed to be, say I'm starting with super Yang Mills forward, that's a CFT that has no quasi-particle excitations. So CFTs, as you know, are characterized by an operator product expansion. So what you can do using the OPE is compute, say, even the conductivity, but only at frequencies much bigger than temperature. So in the remaining time, I'll describe a calculation that we did. So this is what we got from the OPE. We got the high frequency behavior. And then we just postulated that there was some ADS dual theory in ADS Schwarzschild, ADS 4 in this case, CFT3, with a black hole. Now the high frequency behavior is the behavior near the boundary of the ADS 4, where things are under control and black hole doesn't play much of a role. And so you can again match the OPE to what happens in ADS near the boundary. So you postulate some effective gravitational theory, and you have some various coupling constants. And you determine all of those coupling constants using this matching procedure at high frequency. And then to get the low frequency behavior, you really need the black hole. You have to go to the horizon of the black hole. That's where all the dissipation and this gamma and sigma of 0 will be determined by what's happening near the horizon. And so this is a little uncontrolled because you have a lot of choices for the effective theory. You just make some simple choice. In ADS 4, you determine its couplings quite precisely from your knowledge of the OPE, and then use the black hole uncontrolled, but physically very well behaved. It will give you, things that vanish linear in frequency and gives you a sigma 0, finite, and all of that to get the low frequency behavior. And this could also have been done for the Ising model, although we didn't do it. So let me just show you how that works. Okay, this is just a basic review of OPEs that I'm sure all of you know. So it's any CFT is characterized by some scaling dimensions and some OPE coefficients at ABC. So from this, you can to compute the conductivity, you need a 2-point correlation function. And you have to look at it in the regime where frequencies are much larger than momentum. So you just take the OPE of product of the two currents. And at large frequency, it has a term like this. This is even at 0 temperature. The coefficient here is sigma of infinity. That's exactly this number. So this number of sigma of infinity is basically, in fact, that's how Bootstrap computed it. It's just the constant term in the OPE of two current operators. That's sigma of infinity. But you will get corrections, which have a smaller dependence on frequency. And we're only going to keep one correction, actually two, which is just the thermal operator, the most important O, which gives you the leading correction at high frequencies, is the thermal operator, which is just psi squared, with dimension 3 minus 1 of u. Okay, so now let's just take this OPE and look at its expectation value at non-zero temperature. This will be valid as long as omega is much bigger than kT. So now this acquires an expectation value, which is written down here. So B is some number which depends on the normalization of O and C. And therefore, from this, you can write out the behavior of the frequency-dependent conductivity, which is what you measure. Sigma Q is 2e squared over h, and this sigma of infinity that we know so precisely from Bootstrap now. And now there's these coefficients B1 and B2, which I presume Bootstrap can also determine. It's just one more term in the OPE of two current operators. We didn't have that data in 2014. Anyway, I think I'll show you. We determined B1 and B2 by Monte Carlo simulation. Okay. And now the thing is, of course, since these are analytically known as a function of frequency, it doesn't matter whether you have real frequency or imaginary frequency. You can analytically continue. So you can just work in imaginary frequency and get the value of a B1 and B2. And this B2 has to do with yet another term in the OPE, which I didn't write down here. The next term is the stress energy tensor. And so that exactly gives you 1 over omega cubed behavior. So this is for omega much bigger than T. And so you have a lot of data. You just do a Monte Carlo of some model of the superfluid insulator transition. These are the Matsubara frequencies at all integers that you can measure. There's nothing at zero frequency. So the first measurement is here. And actually the whole curve fits very beautifully to these two terms here. Just this term and this term gives you a very accurate fit of the whole behavior, even down to n equals 1. So this is evidence that even n equals 1 is really in the high frequency behavior. Okay, you can try to analytically continue this to real frequencies, and Eric did some of that, and you get some estimates which we don't really believe very much. Anyway, so now you have these numbers, so you know what B1 and B2 are. So the last step is to now match to holography. So this is what we did in this paper, and I think this is a powerful method, can be done for many other systems also, and many other correlators. So we're going to extend OP using holography. So what do we have? We have a CFT, CFT3, which is dual to ADS4, quite generally. And so you go to finite temperature and just take the very simplest black hole, which is the Schwarzschild black hole. So that means the action of the gravity field or the stress energy tensor is just the Einstein action. But now we are interested, this is a CFT with a conserved current. So for every conserved current, there's a gauge field, a U1 gauge field F. So our theory is just going to be, here I've assumed the metric is taken care of, is just F squared. Okay, that's the bare theory, F squared with some coupling constant G4. Okay, so that was what I looked at in my first paper with Dan Sol. Alpha was 0 there. I'll come to what alpha is in a minute. The theory was just F squared. And you compute the conductivity in that theory, and you get this value, this surprising result. So, which is just frequency independent conductivity. It wasn't clear at all as we were doing the calculation, it's going to be frequency independent. But that's what came out, and we understood that through some strange self-duality properties of ADS4 electrodynamics. Basically, electromagnetic duality on 4 dimensions gives you this frequency-independent conductivity. So the sigma of infinity in particular is just G4, the gauge coupling constant in 4 dimensions, which is also dimensionless. So, and since we know sigma of infinity from bootstrap so well, so today we can just put a value for G4. Also, another, when we saw this constant behavior, in naive guesses, oh, well, this is boring. But in fact, getting something constant is really remarkable because the free particle behavior is not a constant. It's called a delta function. So this indicates that this is like an extremely strongly interacting system where there's just a constant conductivity. So it's really the strong coupling nature of holography and the black hole that gives you this constant. Okay, but now we want to do better than just a constant. So we're going to put in the spirit of the OPE, what we've been doing so far is only including this term. So now we want to include this. So there's some scalar, which I call var phi. There's some scalar var phi, which we're going to now add to the theory. It'll have some scalar potential and so on, but we're going to make an even simpler assumption. All we're going to say is we just take a fixed scalar profile so that as u goes to 0, it vanishes on the boundary. The boundary is at u equals 0, the horizon is at u equals 1. So vanishes at the boundary, and this quantity, of course, we also know in bootstrap or whatever, is this. So we know again the value of, in suitable units, the value of this coefficient here. And then finally, I put in the term in which couples phi to the FF. So this phi FF is just a holographic representation of this OPE. This is the OPE between J, J, and phi. So on the holographic side, it's F, F, and phi. In the CFT side, it's J, J, and O. This phi is holographically dual to O. So from knowing this C and knowing the B, you can completely fix the value of alpha. So that's what we did. Now we take this theory, and all we do is just put in a Schwarzschild black hole in here. That's all. So all that matching was done at 0 temperature in ADS4. The calculation to determine alpha and G4 was done in ADS4. You don't even need a black hole then. And then you put a black hole in the background metric and just solve this equation, including the black hole horizon. And then you get actually, so this is what we get. This is the kind of sigma of omega that we get. So sigma of infinity is what we know it to be. And then there's some almost factor of 2 rise. And yeah. So I don't know how accurate this is. It'd be great to have other methods and other approaches. I mean, here we just took a very simple scalar profile, only determined at 0 temperature. I think you could also do a bit better by taking some scalar potential and having the scalar evolve as you approach the horizon. We didn't do it, but we could. That would be a way to improve it a bit. And let's see what that does. I mean, anyway, I think we ran out of steam once we got this result, so we stopped at that point. One of the reasons we stopped was, well, what can we compare with? I don't know. And I think with all these modern developments, and also the experiments now, I think I'm optimistic that we're going to get much better at determining this function. Okay, yeah, so that's the thing we proposed in the paper with Ami Katz for the XY model, and it can also be applied to the Ising model, although we didn't. Yeah, that's really all I have to say. So thank you very much.